Hi guys, so in today's video we're gonna prove that if a function is differentiable at a point C, then it is definitely continuous at that point C, right? So if f is differentiable at x is equal to c, then f is continuous at x is equal to c. So basically what we want to prove is that f differentiable at x is equal to c implies f continuous at x is equal to c, right? So as you can see, this is a P implies Q statement, right? So we have P implies Q. So we're gonna assume P to prove it because we want to use the direct proof to prove this. We're gonna assume that f is differentiable at a point C, right? So this implies that it exists f prime of c, right? And that is equal to the limit as x tends to c of f of x minus f of c over x minus c, right? So we assume f differentiable at x is equal to c. So this implies that this exists, right? Exists a finite limit as x tends to c of f of x minus f of c over x minus c. Now let's see this limit as x tends to c of f of x minus f of c. This one here, this can be written as limit as x tends to c of f of x minus f of c, then we multiply by x minus c over x minus c. This is basically multiplying by 1 because if these two cancel out, we're gonna get the same here, right? So this is done so that we can use properties of limits. So this is basically a product of this one here and this, and we know that the product of the limit of the product is equal to the product of the limits. So basically this is equal to the limit as x tends to c of x minus c times the limit as x tends to c of f of x minus f of c over x minus c. So we have separated these two, right? Now as you can see, this one here would become 0 because basically if we substitute this c inside, we're gonna have c minus c, and that gives us 0, right? And this one here is basically f prime of c, the one we have here, right? So this is basically equal to 0 times f prime of c, right? So which is 0, right? So basically we can see that this one here is equal to 0, right? So let's write it down. So we have the limit as x tends to c of f of x minus f of c. This is equal to 0, right? Now again, we can use properties of limits because we have difference here. The limits of the difference is the difference of the limits. So this implies that the limit as x tends to c of f of x minus the limit as x tends to c of f of c, this is equal to 0, right? Now if we bring this one here on the right hand side, this implies that the limit as x tends to c of f of x is equal to the limit as x tends to c of f of c, and we know that this one here is gonna give us f of c because limit as x tends to c of f of c is basically f of c, right? So this implies that limit as x tends to c of f of x is equal to f of c, and that is exactly the definition of continuity, right? So this implies that f is basically continuous at this point x is equal to c, right? So this implies that f is continuous at x is equal to c. So we have proven that if f is differentiable at x is equal to c, then it is continuous at x is equal to c, which was our goal. One more thing to notice here is that the implication is not true the other way around. So we have differentiable at c implies continuity at the point c, right? But the implication is not true the other way around. This is not true because a function can be continuous without being differentiable at the point, right? So if, for example, one example is the function absolute value, whose graph is something like this. So we can see that this function is continuous at the point 0, right? However, it's not differentiable at this point, right? So the implication, a function can be continuous without being differentiable at the point, right? So we have not continuous at c implies not differentiable at c. However, continuous at c does not imply differentiable at c.